Imagine stepping through an Einstein-Rosen bridge, a tear in space, hoping to find a thriving alien world, only to be spit out into absolute darkness. Every star and planet here has been pulverized into a hyper-dense, inescapable soup. In this alternate reality, gravity is so overwhelming that matter is violently crushed inward, leaving no room for life or complex structures. Returning home, you'd find a reality that looks like a statistical impossibility. Compared to that hostile expanse, the gravity in our universe is bizarrely, almost suspiciously weak. You can see the scale of this anomaly by using a tiny household fridge magnet to pick up a paperclip. That small sliver of magnetic material is successfully fighting the gravitational pull of the entire planet Earth. Looking at this fragile blue Earth floating in the void clarifies the stakes. If gravity were even slightly stronger, stars would burn through their fuel in a few million years rather than billions, and biological structures would be crushed under their own weight. This weakness isn't a glitch, it's the mandatory condition required for human life to exist. The odds of hitting these exact settings by chance are effectively zero, unless our universe is just one outcome in a much larger series of experiments. Eternal chaotic inflation suggests the Big Bang was a process of unrelenting exponential growth. Space expands forever, but specific pockets eventually cool down, forming isolated bubbles. Because each cools independently, random quantum fluctuations set unique laws of physics for each region. When we observe these pink star-forming regions in our sky, we are looking at the successful results of our specific laws. We occupy one habitable bubble adrift in a much larger, chaotic multiverse. Our presence here is a statistical inevitability. In a multiverse of infinite variation, we exist because we are in the specific bubble where the laws of physics allowed us to evolve. But what is the actual mechanism that causes gravity to fluctuate so wildly from one bubble to the next? This is where we look to M-theory. To make the math of the universe work, this framework requires 11 space-time dimensions, dimensions that unfold far beyond the three-dimensional space we experience. In this brand world scenario, the multiverse is like a massive office building. Our entire universe is just a single glowing plane, or one floor, floating within a higher dimensional bulk. Most fundamental forces, like the electricity powering our world, are permanently glued to our specific floor. They have no way to reach the other levels. But gravitons, the particles carrying the force of gravity, are different. They are uniquely unbound, meaning they can leak off our plane and drift into the extra dimensions of the building. Gravity appears weak to us because its total strength is being continuously diluted across that vast higher dimensional expanse. This constant bleeding of energy into other dimensions is the reason our gravity doesn't crush us. It is the precise mechanical reason we are able to survive. Standing at the edge of our hospitable brain, we are left looking out at the vast, unreachable bulk of the multiverse. If the forces that define us are trapped on a three-dimensional plane, how could we ever prove that other bubbles even exist? The solution lies in extreme physics. We would need to tunnel through the fabric of space itself using Einstein-Rosen bridges. A wormhole curves and warps the fabric of spacetime, potentially patching two separate universes together through a central bridge. These transit systems could theoretically bypass the higher dimensions entirely, allowing us to move directly from our bubble to another. We are one bubble in an infinite, boiling sea. But the same precise laws that allow us to exist also give us the capacity to look up, ask questions, and map the multiverse.